Finding the state sequence, we now move on to the second problem, that of finding the state sequence Q equals to Q1, Q2, Q3 until Qt, having the highest probability of generating observation sequence O equals to the sequence O1, O2, O3 until OT, given the model lambda. Let us define gamma t of I as the probability of being in state Si at time t, given O and lambda, which can be computed as gamma t of I equals to the probability of Qt equals to Si conditioning on O and also parameter lambda, which by the definition of the conditional probability will be the probability of O conditioning on Qt equals to Si lambda times the probability of Qt equals to Si conditioning on lambda divided by the probability of big O conditioning on lambda. And if we expand the term of the definition of the three conditional probability, that will be the probability of O1, O2, O3 until OT conditioning on Qt equals to Si and lambda times the probability of OT plus 1 and so on until O capital T conditioning on Qt equals to Si lambda, then times the probability of Qt equals to Si conditioning on lambda, divided by sigma of the probability of O Qt equals to Sj conditioning on lambda, summing for all index j starting from 1 to capital N, and which is equals to the probability of O1, O2, O3 until OT and Qt equals to Si conditioning on lambda times the probability of OT plus 1, OT plus 2, and so on times the sequence of big OT conditioning on Qt equals to Si and lambda divided by the sigma of the probability of O conditioning on Qt equals to Sj lambda times the probability of Qt equals to Sj conditioning on lambda, summing for index j starting from 1 to n, which is equals to alpha t of I times beta t of I divided by sigma of alpha t of j times beta t of j, summing for index j starting from 1 to n. And here we see how nicely alpha t of I and the beta t of I split the sequence between them. The forward variable alpha t of I explains the starting part of the sequence until time t and ends in Si, and the backward variable beta t of I takes it from there and explains the ending part until time t. Now the numerator alpha t of I times beta t of I explains the whole sequence given that at time t the system is in state Si. We need to normalize by dividing this over all possible intermediate states that can be traversed at time t, and I guarantee that the sigma of gamma t of I summing for index I is equals to 1. To find the state sequence for each time step t, we can choose the state that has the highest probability, that is Qt star equals to the argument of a maxima of gamma t of I, where the maxima is taken among all index I, and by this may choose Si and Sj as the most probable states at time t, and t plus 1 even when Aij equals to 0. To find the single best state sequence path, we use the Viterbi algorithm based on the dynamic programming, which takes such transition probabilities into account. And a given state sequence Q equals to Q1, Q2, Q3 until Q capital T, and observation sequence O equals to O1, O2, O3 until big O of T, we define the delta T of I as the probability of the highest probability path at time T that accounts for the first T observations and ends in Si. That is, delta T of I is equals to the maxima chosen among Q1, Q2, Q3, and the Qt minus 1 of the probability that Q1, Q2, Q3 until Qt minus 1 given, and Qt is in the state Si, and also with the sequence O1, O2, O3 until OT with the observation sequences conditioning on the parameter lambda. Then we can recursively calculate the delta t plus 1 conditioning on I, and the optimal path can be read by backtracking from t, choosing the most probable at each instant. The algorithm is as follows. There are several steps: initialization, recursion, and termination. And also the fourth is a path state sequence backtracking. Okay, now initialization is easy. We just set up delta 1 of I equals to pi I times pi of O1, and we set up phi 1 of I equals to 0. The second step of the algorithm is the recursion. We set up a delta t of j equals to the maxima of delta t minus 1 of I times aij times bj of ot, where the maxima is taken among all possible I, and the phi t of j is equals to the argument of maxima of delta t minus 1 of I times aij. Again, the maxima is taken among all possible index I. Now, the third step is determination. P star is equals to the maxima of delta t of I, where the maxima is taken among all possible index I, and the qt star is equals to argument of maxima of delta t of I, where the maxima is taken among all possible I. The fourth step is the path of state sequence backtracking, where qt star is equals to phi t plus 1 of qt plus 1 star. And t is the index of capital T minus 1, capital minus T minus 2, and so on, decreasingly until it reaches T equals to 1. Using the lattice structure of figure 15.2, phi t of j keeps track of the state that maximizes delta t of j at the time t minus 1, and that is the best previous state. The Viterbi algorithm has the same complexity with the forward phase, where instead of the sum, we take the maxima at each step.